It's not a comprehensive review of all of Calc 1, but it should be a nice refresher to think through some of the rules and functional derivatives. I would recommend going back and reviewing some of the sections in more detail if they seem unfamiliar to you. So to start with, I'm going to talk about graphs of derivatives and graphical interpretations. I'm also going to do a quick review of derivatives of various types of functions, as well as some examples. We're going to look at polynomials, trigonometric functions, exponential functions. And then finally, I'm going to finish the video with derivative rules, which includes product rule, quotient rule, and chain rule. So to start, let's talk about what a derivative is graphically. Suppose I start with some generic function. I'm going to call this function f. The derivative is a measurement of the slope of the tangent line at a point on f. So I'm going to pick an arbitrary point, call this point x, and the derivative is going to be the value of the slope of this tangent line. And my notation for that is going to be f prime of x. And at this point we see that that value is negative. And at different places along this graph you can see that the slopes are negative through here, 0 here where the curve is flat, and then positive along the other side. So graphically I'm thinking of the rate of change of my function f at each of these places. I can also think of graphing my derivative function. And in order to do that, this is going to be a rough graph because I don't have full information about what the formula for my original f function is. But what I can do is find the places where my derivative function is equal to 0. This is a place where f prime is equal to 0 because the slope of this tangent line is flat. I also have, and this is called a critical point, maybe I'll label this. It's a critical point of my original function f, and it's going to be a 0 of my derivative graph. Similarly, I see at this point I have a horizontal tangent line, and so my derivative function is also going to be equal to 0. And I can weave in between using the fact that the slopes of this graph are negative, so I know my derivative curve has to be below 0. So I'm going to sketch in just approximate, and I don't know how, this might be a slope of -5, so my derivative graph should be down at -5. I'm not doing this with that much accuracy. But I do see that along these values, my original function has a positive slope, and it looks like that slope starts leveling out off because this looks like a line with constant slope. Constant sort of steep slope. So I'm going to see this as having a positive slope and then leveling off to a constant value. And maybe I don't have enough information. I also have a positive slope of the tangent lines, so this is going to be above 0. This is a quick refresher of how to think about graphing a graph of a derivative curve based on the original curve. I looked for the critical points, the place where my original curve was flat, equal to 0. I looked for the places where my original function was increasing. That's where these values are positive. And I looked for places where my original function was decreasing. That's where my derivative values are negative. Next, let's look at some derivatives of polynomials. So, what's the derivative of a constant function? Well, what is a constant function? Let's say I'm going to want to know what is the derivative of the number 3. So in my head, I'm thinking of 3 as a constant function. Here's my graph, that for any x value, my output, my y value, is going to be equal to 3, which gives me a horizontal line. Based on our previous discussion, we know that the derivative is a measurement of the slope of this line. The slope of this line is 0 because it's a flat line, and it means that the derivative of constants is always 0. And it could be any constant. We could do even a crazy constant like pi is actually just a fixed number, 3.14159, and so forth as a decimal approximation, and the derivative of that number is 0. Other important functions are linear functions. This is a special boring type of polynomial. What's a linear function? Something like this. Let's say that x in this case is equal to 5x plus 1, and I want to know what is the derivative of the function 5x plus 1. In this case, and in every case, because it's the sum of terms, I can take the derivative of each of the terms individually. That's another rule of derivatives. This is the same thing as the derivative of the first term, 5x, plus the derivative of the second term, 1. Or I could think of it holistically as, what is the slope of this line? The slope of this, the tangent lines are exactly equal to this line, and this line has slope 5, so I know that the derivative should be equal to 5. And that works out when I take the derivative of each of the pieces as well. The derivative of this function, 5x, is going to be equal to 5, which is also the slope of the line that's centered at the origin. And the derivative of 1 is just equal to 0 because 1 is a constant. Which is equal to 5. This is sort of my graphical check that I arrived at the same value. So in general, taking the derivative of linear functions, it's always going to be the slope of the function. Let's get to more complicated functions, and we're going to talk about power rule. Power rule, derivatives of polynomials. Power rule only applies to polynomials. Polynomials are functions of the form, maybe I'll call this f of x equals ax to the n, and I can have multiple terms with different coefficients and different exponents, where these are numbers and these are numbers, and the x is the variable. And if I want to take the derivative of this function, I'll introduce another notation. So another way to write the derivative of the function is to say f prime of the function is equal to, I'm going to take this coefficient and it becomes n times a times x to the n minus 1. And this is something that we typically memorize as power rule. I'm not going to talk about the derivation because this is just a review video, but it's something that's worth looking into. Let's look at an example of this. We'll do a couple of examples. Suppose our original function f of x is equal to x cubed. Then the derivative of this function, by following power rule, the exponent becomes a coefficient in front, and the previous exponent, I'm going to subtract 1 from it, and I'll end up with a 2. Second example, let's say I had a fractional exponent, and let's also say that I had some initial coefficient of like 7. So let's say I want the derivative of 7x to the 1/2. Following the same power rule, I'm going to bring the power down in front and multiply it by 7, so I end up with 1/2 times 7 times x, and I'm going to subtract 1 from 1/2, and so in my head I might think to myself, what is 1/2 minus 1? That's going to be negative 1/2. And it works even though we're using fractions and negative values. I end up with this as my derivative, which I could rewrite if I wanted to, that 7 divided by 2 becomes 7/2, and x to a negative power is the same thing as placing it in the denominator. And 1/2 is the same thing as the square root. So this is another way to rewrite it. You can memorize this as power rule, the most basic derivative rule. We also want to know about derivatives of trigonometric functions. And the derivative of sine function is possibly the most basic function, and it ends up as an identity being cosine of x. Again, I'm not talking about the derivation, but I will talk about a way to remember this. I always remember this by thinking about the graphs of these two functions. So when I think about the sine function, I know the sine function starts at 0 and it's periodic with this sort of loopy behavior. So in black, this is my sine function. And I know that the derivative of this has to start at a positive value, and the derivative is positive until I get to here where it's 0. So in my head, when I think about the derivative of the sine function, I always think to myself that it starts positive. And when I compare that to my cosine function, notice for the cosine function, that's the function that starts up at 1 and does the same, whoops, these don't align. Oh no, I didn't line them up. Should be 0 there and 0 there. I'll loop it until it's 0 there. So this function starts with positive slope, and this function starts with negative slope. And I'm sloping downwards through here, and that's how I remember that the derivative of my cosine function is going to be the negative of the sine function. It's because it starts up at 1 and starts off with a negative slope. So it's good review. Rather than going through the derivations of each of these, I think it's important to see this table that we just discussed how the derivative of sine is equal to cosine. The derivative of cosine is equal to negative sine. Also, we can use quotient rule, which I'll do in just a little bit, to find out that the derivative of tangent is secant squared. And then these following trig derivatives are important to know, but they're also ones that you could figure out using quotient rule, which we'll talk about in just a second. Next, I'm going to talk about derivatives of exponential functions. What is an exponential function? It's a function that has variables in the exponent. And our favorite one of these in calculus is our function f of x is equal to e to the x. This is an exponential function because my variable x is up in the exponent. The reason why we like it is because the derivative is equal to itself. And again, we could analyze this graphically to understand why that's the case. Exponential functions are functions that look like this. And in this case, at any given x value, the slope is also equal to that value. So for example, if I pick a value of x equals 0 and plug that into this function, e to the 0 is 1, I have a slope of 1 right here. If I plug in some negative number, e to the negative 1, let's say, the slope, the height is going to be the same as its slope. And in this case, it's a very gentle slope, a fractional slope. And the height of the function up here is also equal to its slope, that it's a big height and also a steep slope. What happens if we have another value in the base? Let's say that we have 2 raised with a variable in its exponent. This is another exponential function. The derivative of this function is very similar. It's also going to be 2 to the x, but I also have to multiply this by a scaling coefficient, the natural log of 2. This is supposed to say natural log. And in general, it's always the case that if I have some exponential function a raised to the x power, my derivative is going to be that same function over again times a scaling factor that will shrink it or stretch it, the natural log of a. And notice if e were in the base here, we get e to the x times the natural log of e, but the natural log of e is just 1, and that's why we have our self-replicating function here. Let's move on to talking about various rules that we use when working with derivatives. I already mentioned one is that each of the terms in a sum can be taken individually. That doesn't work for products, however, and this is one of the often missed derivative rules. That if I have the product of 2 functions, so that means that one function is being multiplied by the other function. That's what a product is. A product is a multiplication problem. And I want to take the derivative of this product. The derivative of the product is going to be, instead of just taking the derivative of each of the pieces, which is what we would like, we have to worry about the little slippage in between. And I'm not going to go into a lot of detail in this video. I would check out a video on product rule if you are unfamiliar with this. It's going to be the first function times the derivative of the second function plus the derivative of the first function times the second function. And notice it doesn't matter which order you do these terms in. All that matters is that the original function is being multiplied by the derivative, and then the other original function is being multiplied by the other derivative. By the commutative property of multiplication and the commutative property of addition, you could do it in whatever order you would like. Let's look at an example of this. Let's say that I want to know what is the derivative of x to the fourth times the sine of x. Notice that this is a really classic product. I have two functions multiplied by one another. I'm going to do a little scratch work on the side to say that in this case, my first function is x to the fourth. My second function, g of x, is going to be equal to the sine of x. And I can see that the derivative of the first function by product rule is 4x cubed, and the derivative of the second function is going to be cosine of x, because it starts positive. And using all of this information, I can now apply product rule to find the derivative. The derivative is going to be the first function, x to the fourth, times the derivative of the second function, cosine x, plus the derivative of the first function, 4x cubed, times the function, sine of x. And notice there are some things that we can do to simplify this, but just for clarity in this video, I'm going to leave it like this. Next rule I want to talk about is quotient rule. Quotients happen when two functions are being divided by one another. So the derivative of the quotient of two functions, f of x divided by g of x, is given by quotient rule. There are a couple of caveats. I should put a little star up here. That it's only going to be the case for values for which g of x is not equal to 0. If g of x were 0, then this isn't going to be defined. So the derivative quotient rule, the way that I remember it, is by the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. Some people memorize it as low d high because the low is in the bottom, and d high stands for the derivative of the high function, minus high d low, all divided by low squared. I want to point out here that order does matter. Unlike the product rule, in which we could use the commutative property to switch around the order of the terms, because this is subtraction, we need to make sure that this term is being subtracted, and so we have to go in this order. Let's look at an example, and the example that I want to use is tangent from our previous trig work, because I think that it's an interesting application. So recall that by trig identities, that tangent, the function, is equal to sine of x divided by cosine of x. Now I didn't take the derivative yet, I'm just rewriting my tangent function by doing a trig substitution. And now that I know this, I can apply my quotient rule to be able to find the derivative of this. Work at the side to make sure that we keep things clear. In this case, our top function, f of x, is going to be sine of x, and the bottom function, g of x, is cosine of x. And the derivatives of each of these pieces, the derivative of sine is cosine, and the derivative of cosine, recall, is negative sine. So now that I've done this scratch work, I'm going to set myself up to be able to apply quotient rule. So for I need to take the bottom function times the derivative of the top function, and the derivative of the top function here is the derivative of sine, which is cosine, minus the top function, which in this case is sine, times the derivative of the bottom function, the derivative of cosine is negative sine, divided by the bottom function squared, which in this case is cosine squared. And I'm writing this squared in here. It's standard practice when dealing with trig functions that when you square them, you put the 2 inside so it's confused with the cosine of x squared. And we're going to simplify this. We end up with cosine squared x plus sine squared x all over cosine squared x. This is the one trig identity that I want everyone to have memorized, that by the Pythagorean theorem, cosine squared plus sine squared is equal to 1, because each of these are the side measures of a right triangle. So I end up with 1 over cosine squared x, which is a perfectly reasonable answer, but we tend to write as secant squared x. The derivative of tangent is secant squared x. Last but not least, we're going to talk about chain rule. Chain rule, instead of having a product of two functions multiplied by one another, this happens when we have one function within another function, the composition of functions. So suppose I have my f function, and within my f function I have another function g, and I want to take the derivative of this. The derivative of a composition of functions is going to be the derivative of the outside function evaluated at the inner function times the derivative of the inner function. And again, I have more detail in a different video, but this is supposed to be our quick summary. Let's look at an example. A classic example could be something like the cosine of x squared. So in this case, notice that cosine is my outer function and x squared is my inner function. This is not multiplication. This is a composition of functions because my x squared function is being put into cosine as an operation. So following my rules, I see that it's going to be the derivative of the outer function. The derivative of cosine is negative sine. Evaluated at the inner function is x squared. And then I'm going to multiply that by the derivative of x squared, and the derivative of a polynomial by power rule. The 2 comes down in front, and I'm left with this as multiplied by 2x. One more example, because these are some of the more difficult types of whoops! Get my notation. I was taking the derivative of this function is equal to this. Clearly these two things are not equal. So let's consider another derivative. I want to look at the derivative of the square root of e to the 2x plus 5. And I'm going to do this in a couple of steps. So to get started, I need to identify what is my outer function and what is my inner function. And to help with that work, I'm first going to rewrite this. For me, visually, I like to think of, instead of using square roots, I like to think of them as fractional exponents. So this is the same thing as e to the 2x plus 5 all square rooted. So now it's a little easier to see that my outer function, f of x, is what's going on the outside here. The very most thing on the outside is that all of this stuff is being raised to the 1/2. And maybe it's more helpful even to see this as a different variable. I'll call it alpha to the 1/2, because this whole thing, the inner piece, is the alpha. And then g of x is going to be the inner piece, which is e to the 2x plus 5. So now I can apply chain rule. And in this case, recall that chain rule is going to be the derivative of the outer function, and the derivative of alpha to the 1/2 is going to be 1/2 of alpha raised to the negative 1/2. By power rule, the 1/2 is coming down in front, and I'm subtracting 1 from 1/2 to end up with the negative 1/2. But what goes on inside here is going to be g of x, the function that I was evaluating this at. So the inside stays as e to the 2x plus 5. But we aren't quite done. So this is the derivative of the outside function evaluated at the inside function. Now I need to still multiply by the derivative of the inside function, and for the derivative of the inside function I'm actually applying chain rule again. The derivative of e to the 2x is going to be e to the 2x times the derivative of 2x, which is 2, plus the derivative of 5, which is 0. So altogether, all of these things multiplied, I have e to the 2x times 2 times 1/2. The 2 times 1/2 simplify to be just 1. And I'm left with e to the 2x plus 5 to the negative 1/2 times e to the 2x. It's my final derivative, is my answer.